All right, so let us begin today's tutorial session. So this is session number 5. So we were solving problems based on the power distribution reliability indices, and in this today's session we are going to solve problems based on the reliability for repairable and non-repairable components in series or parallel combination. So before that, I would just go through the some of the important terms that will help you in solving the problem. So let us see what are the some of the important things we have to just recapitulate or we have to keep in mind so that we will not face any problem while solving the problems. So we usually denote the mean time to failure. It is abbreviated as MTTF M bar, that denotes average. It is the reciprocal of mean failure rate lambda. Lambda is the mean failure rate. And similar, in the same way, we can define mean time to repair. So we denote it as R bar. It is the reciprocal of mu, and mu is the mean repair rate. And the mean time between failure is the summation of mean time to failure plus mean time to repair. Mean time between failure, it is also, we can say it as mean cycle time T bar. So it is the summation of M bar plus R bar. So let us see the first for the repairable components in series. Reliability of repairable components in series. So in this, if we combined, we want to find the mean time to failure for the combined system. mean time to failure. So you can either denote it as M bar system, or I have denoted here M bar series. So it is the reciprocal of summation of lambda I. Lambda is the mean failure rate for each component that are connected in series combination. Similarly, for finding out the mean time to repair for the system, that I can denote it as R bar series. So it is reciprocal, it is the ratio of lambda I summation of lambda I to the lambda I ri to the summation of lambda I, and in the and consecutively we can define the mean time to failure and mean time to repair for the components connected in parallel combination. So for the parallel combination we can write mean time to failure in parallel, it is equal to 1 plus summation lambda I ri divided by multiplication of lambda I, then summation of sigma ri. And mean time to repair for parallel components, we can say it as ratio of multiplication of ri to the summation of ri. So, so these are the basic things we should at least keep in mind. Now let us start to solve the first problem of today's session. So this is common data for problem from problem first to third. Common data from for question 1 to third. So a radial distribution feeder consists of three sections of 3 kilometer length each. Each feeder section suffers of 2 faults per kilometer in 10 years. The average repair duration for each feeder section is 1.5 hour. So you have to determine the average repair duration of the feeder. So what are the things we have given? So you can write down here. So this is a problem based for the repairable components connected in series. So just you have to apply the formula and get the answer. So we have given mean failure rate for each feeder section as mean failure rate of each feeder section. How we can write? It is given as each feeder section suffers two faults per kilometer in 10 years. So, and each feeder section is of 3 kilometer length. So how many number of faults will be there for 3 kilometer? 2 cross 3, 6 faults. And if you want to find out for each year, then you have to divide it by 10 because it is the number of faults in 10 years. So it will give you 0.6 faults per year. So this is the mean failure rate of each feeder section. So it is identical for all the three sections. We can write it as lambda 1, lambda 2, and lambda 3 is equal to lambda, that is 0.6. And next we have given average repair duration. So you can write it as mean time to repair for each feeder section is 1.5 hour. So that means we can say it as R1 is equal to R2 is equal to R3 is equal to R, that is 1.5 hours. So we apply the formula for mean time to repair for the repairable components connected in series. So mean time to repair of the feeder so R series, we can say it as R series is equal to ratio of lambda I Ri divided by ratio of lambda I. Lambda 1 R1 bar plus lambda 2 R2 bar plus lambda 3 R3 bar divided by lambda 1 plus lambda 2 plus lambda 3. Since these all are equal, so whatever value we will get R bar only. So this will comes out 1.5 hours. Correct answer for this problem number 1 is B, 1.5 hour. So how many of you are able to solve this problem? And who is solving, who are getting answer, they can type your answer in the chat box so that I can also see. Yes, I got one response. Now let us see the next problem. So the next problem is that for the same data you have to find out the failure rate of the feeder. So you have to find out the lambda series. you have to find out the failure rate of the feeder. Lambda series. This is the summation of all the individual components sigma lambda I. So this will be lambda 1 plus lambda 2 plus lambda 3. Since all three are have identical failure rate, so it is 3 lambda. And lambda we have calculated as 0.6 faults per year. So 3 into 0.6, it will give you 1.8 faults per year. Correct answer will be option C. Yes, C the correct option. Murli Pedro. In the next problem, we have to find out the availability of the feeder. So either you directly write down the equation for availability of the feeder, and you can also first find out the unavailability of the feeder, and then just subtract it from, if you're finding out in 100 in percentage, then subtract it from 100, and if you're finding out in unit form, then subtract it from 1. So for here I am just starting it from unavailability of the feeder. So first I will find out the unavailability of the feeder. So unavailability is defined as it is the ratio of mean time to repair to the mean time between failure. So if you just write again, so it is the mean time between failure is the summation of mean time to repair plus mean time to failure. So this will give you. So here I am finding out the for the whole system. So I can write that mean time to repair is R bar series, and then R bar series plus failure is M bar series. So we don't know about we already found out this R bar series mean time to repair. We don't know that mean time to failure. So in order to find out the mean time to failure, we can write mean time failure is the reciprocal of mean failure rate. So it is reciprocal of 1 divided lambda series. So we know that lambda in the calculated in the last problem, lambda is comes out as 1.8 1.8 faults per year. So it will give you years per fault. So here we need to just take care of the units. So we will convert this year into hours. So it will be 8760 divided by 1.8 hours per fault. So mean time to failure will be comes out this much. So we can write here U is equal to 1, R bar series is 1.5 hours, and this one is 1.5 hours, and this one is 8760 divided by 1.8 hours. And in order to find out in percentage from, sorry, here the options are incorrect. I think I have not updated the options here. You can write it as 99.99%, 99.98%, 99.96%, 96 is too close, 99.92%, and 99.97%. So this is the correct options for this question number 3. Here you have to find the ability feed in percentage form. So multiply it with 100%. So it will give you 0.0308%. So just you have to find out the availability of feeder. I have found out this unavailability of feeder, and from the options you can type your answer in the chat box. So I got some responses. D is the correct option. Yes. Finally, the availability of the feeder we can write A is equal to 100 minus U percentage. So 100 minus 0.0308. So this will give you 99.97%. Option D is correct. So the common data type question is finished. Now we will solve individual type question. So the next problem is if a unit is having failure rate of 0.6 faults per year, determine its mean time to failure in hour. Failure rate is given, you have to find out the mean time to failure, that is m bar. You have to find out the m bar. So in this problem it is given that mean failure rate that be denoted as lambda, it is given as 0.6 faults per year. You have to find out the mean time to failure. It is the reciprocal of mean failure rate. Just take care of the units. Mean time to failure MTTF. It is m bar. It is the reciprocal of lambda 1 divided by 0.6. It will give you the time in years. So you have to find out it in hour. So multiply it by 8760 hour per fault. So this will give you answer as 14,600 hours per fault. So the correct answer will be B. 14,600 hours is the mean time to failure. How many of you are given the correct answer? Yes. Anu, Pedro, Murli, all are correct. Now let us see the next problem. Again, it is the common data for till question number 7. So common data for question 5 to question 7. So it is given that there are two electrical motors operating in parallel to form a unit, and the failure rates of the motors are 0.8 faults per year and 1.25 faults per year, and the repair durations are 6 and 8 hours respectively. And in the question 5, you have to find out the average repair duration of the unit. So this problem is based for the components, repairable components connected in parallel form. So whatever we have seen in the first slide, we have to follow that. So first we will write what are the given things here in this problem. Mean failure rate of motor 1, mean failure rate of motor 1 is be denoted as lambda 1. It is 0.8 faults per year. And similarly, we have given the data for motor 2. So mean failure rate for motor 2, lambda 2, it is given as 1.25 faults per year, and the repair durations are 6 and 8 hours. So mean time to repair is also given. Mean time to repair for motor 1 R1 is 6 hours, and mean time to repair for motor 2 R2 bar is 8 hours. Here we have to find out the mean time to repair of the unit, that is average repair duration. Mean time to repair for the unit for the system, we can say R bar parallel. For parallel components, we know that it is the ratio of multiplication of Ri bar to the summation of individual mean time to repair Ri bar. So there are two components connected in parallel. So R1 into R2 divided by R1 plus R2. R1 into R2 is 48 divided by 14. 8 plus 6, 14. So it will give you mean time to repair for the combined system 3.43 hours. Correct answer will be B, 3.43 hours. Yes. Murli, Anu, Pedro, all of you are correct. Correct answer is B. Now let us see the next problem based on the similar data. So in this problem we have to find the availability of the unit. So first you can directly put the equation for the availability of the unit. Otherwise you can first find out the unavailability of the unit and then find out the availability of the unit. So first I will find out the unavailability of the unit. So we know that unavailability of the unit is it is R bar parallel to the ratio of M bar parallel plus R bar parallel mean time between faults. So we know that R bar parallel is 3.43 hours. Now we need to find out the mean time to failure M bar parallel. Then we can find out the unavailability of the unit. So M bar parallel, it is the this equation for M bar parallel is 1 plus summation of lambda I Ri bar divided by multiplication of lambda I summation of Ri bar. Here there are two components, so we can simplify it as 1 plus lambda 1 R1 bar plus lambda 2 R2 bar divided by lambda 1 lambda 2 into R1 bar plus R2 bar. So in this problem we have given as the failure rate in faults per year. So we will just lambda 1 lambda 2 are given in faults per year. So when we are putting the values in this equation, just be careful about the units. We have to put it in hours. So lambda 1 and lambda 2 are given in faults per year. So we will put all the values in hour form. because these are in hour from R1 and R2 are in hours. So we will we are going to put all these values. These values are already given. So we can write 1 plus lambda 1 is 0.8 faults per year. So if you put it in our form, 0.8 divided by 8760, that will give faults per hour. R1 bar is 6 hours plus lambda 2 is given as 1.2 faults per year. So divide it by 8760 to get in our form, and the 8 is the number R2 bar, and reciprocal is lambda 1 0.8 into 8760 into 1.25 8760 into R1 plus R2. So doing all simplification, you will get 8760 square plus 6 into 0.8 4.8 plus 10 divided by 0.8 into 1.25 into 14, 7.667 into 10 power 7 divided by 14. So this value comes out as 5481258.2 hours per fault. The mean time to failure is, it is very much high, 54,81,258 hours. Now we will get the unavailability of the feeder. So unavailability of the feeder is R bar parallel is 3.43 divided by 5481258.2 plus R bar parallel is 3.43. In order to get in percentage form, multiply it by 100%. So you will get 6.25768 into 10 power minus 5%. It is very small value. So availability of the feeder, availability of the unit will be 100 minus u percent. So we will get 99.99937. So you can say it as 99.999%. It is the availability of the unit. So correct answer will be A. It is little bit calculative, but no problem. You can easily calculate. So yes, Murli, Anu, all of you are correct. Now let us see the next problem. Sorry. So the next problem is that you have to find out the failure rate of the unit. We have already calculated the mean time to failure. So what will be the failure rate? It is just reciprocal of mean time of failure. So you can say failure rate of the unit, failure rate of the unit lambda will be reciprocal of mean time to failure 1 divided by m bar. We have already found out the m bar. M bar is 54 lakhs 81,258.2 hours per fault. So unit will just reversed faults per hour. Sorry, it will be faults per hour. And again here you have to find out in the faults per year. So multiply it with 8760. So you will get the answer in faults per year. 0.00159, so approximately equal to 0.0016 faults per year. Yes, only two are responding. The correct answer will be B. So correct answer is B, 0.0016 faults per year. Now let us see the next problem. The next problem is, which of the following is not a short duration power quality problems? Voltage sag, swell, over voltage, or voltage flicker. So just you type your answer in chat box. What should be the answer for this problem? Short duration power quality problems. Here it is asked. If you see the short duration voltage variation, that means it sustains for a few cycles till up to 1 minute. And for long duration voltage variation, it sustains for more than 1 minute. So from there you can estimate. So what is the which of the following is not a short duration power quality problems? Yes, see, over voltage is the long duration voltage variation. Some of the important short duration voltage variations you can write that are very familiar, like voltage sag, voltage swell, and interruptions. And on other hand, for long duration voltage variations, we can say that over voltage that sustains for more than 1 minute, over voltage, under voltage, and sustain interruption. Over voltage, under voltage, Sustained interruptions are some of the examples for long duration voltage variations. So from these options, over voltage comes under the category of long duration. So correct answer will be over voltage. So next problem is which of the following components will be present in balanced three-phase voltage? Positive sequence voltage, negative sequence voltage, zero sequence voltage, and the last option is all of these. What do you think? I accept you all from that you are able to give the answer for this question. Which of the following components will be present in balanced three-phase voltage? Positive, negative, zero, or all of these? Which sequence voltage will be present in balanced three-phase voltage? It is very simple problem. Yes, only positive sequence voltage will be present. And in unbalanced system, these components comes into the picture. So if you go through the Fortescue theorem, you can easily find the solution. So the positive sequence voltage will present only in the, will only present in the balanced three-phase voltage, and the negative and zero sequence comes under the picture for the unbalanced system. Now let us see the next problem. Next question is that the difference between the facts and the custom power devices is, and one important thing is that it has multiple correct answer. So question number 10 is multiple select problem, you can say. So multiple answers can be possible. So which of the options can be true for these facts and custom power devices? The first option is facts devices are used in power transmission networks and custom power devices are used in power distribution networks. And the B option is facts devices are used in power distribution networks and custom power devices are used in power transmission networks. And the C option is fact devices are constructed and controlled to work in unbalanced system and the custom power devices are constructed and controlled to work in balanced system. And the last option is fax devices are constructed and controlled to work in balanced system, while the custom power devices are constructed and controlled to work in unbalanced system. So it is capital, it is not a small. So what will be the correct answer for this problem? A and D, Murli, Anu, Pedro, all of you are correct. Yes. Fax devices are used in power transmission networks while custom power devices like we have Bell familiar devices are. Can you tell some of the custom power devices? We have DS Statcom, DVR, and UPQC. These are one of the these are the three custom power devices well known and widely used in the distribution system. And fact devices that means for transmission system only. So A option is correct, and the And for this, and similarly, you can say in that since our transmission system is balanced system, so the facts which only is constructed and controlled to work in balanced system. On the other hand, custom power devices are constructed and controlled to work in unbalanced system, since the distribution systems are generally unbalanced system. So transmission systems we have usually balanced system, we considered as balanced system, and distribution systems are unbalanced in nature. So, so the correct option are A and D. Now let us see the next problem. So in this problem, you have to find out the equivalent reliability of each of the system configurations shown in the figure. An individual reliability is given like 0.900. First, I want to tell you that first you start it from A, and this A problem. I start it from A, and, and whoever is able to get answer, then just type your answer in chat box. 0.99 and R3 0.95. So take it as R1, R2, R3. So for the series configuration, you have to find out the equivalent reliability. Series configuration are equivalent. So for the series combination, we know that it is directly multiplication of individual reliability. So R1 into R2 into R3. So 0.90 into 0.99 into 0.95. So this value comes as 0.84645. And whoever able to solve it correctly, solve for second problem, 11b. Yes, Murli have given the correct answer. Anu, your answer is not correct. So it is always less than 1. So it will never be greater than 1. Now solve it for series parallel combination. B problem. For 11b, how we will approach? First, we will find out the series. Like suppose in this B problem, we have taken this one as R1, R2, R3, R4. So in B problem, first we'll find out R equivalent 1, R1 into R2, 0.9 square. So it will give you 0.81, and R equivalent 2 will be 0.98 square. It will 0.9604. And for parallel combination, now we have like this. This value is 0.81, and this value is 0.9604. Now you have to find out the equivalent reliability. Equivalent reliability will be, we know that for parallel combination, how you write the equation? 1 minus 1 minus 0.81 for the first component, and for the second component 1 minus 0.9604. So it will be equal to 0.992476, equivalent is equal to 0.9925. So the correct answer for this 11B is 0.9925. How many of you are able to get it? Yes, 0.9925. Only Anu has responded. Similarly, you will, I just, you start solving this problem 11C for the parallel combination. So in the C problem, we have given as for the first component 0.60, 0.90 and 0.70. All are connected in parallel form. Zero point 0.99, sorry. This is 0.99. 0.60, 0.99, 0.70. Parallel configuration. For the parallel configuration, how we find out the reliability? Yes, 0.60, 0.90 and 0.70. R equivalent will be 1 minus, for each component 1 minus 60, then 1 minus 0.99 and then 1 minus 0.70. So 1 minus 0.4 into 0.01 into 0.3. So it will come as 0.9988. For parallel combination, R equivalent always comes greater than each individual components, and for series configuration, R equivalent always comes lower than the series, or lower than all the series values. So we are getting here 0.9988 since, and all the individual terms are lesser than that. Similarly, for series terms, you can see that we are having R1 0.90, R1, R2 0.99, R3 0.95, and we are getting 0.84645 because it always comes lesser than individual terms. So keep in mind, whatever answer you are getting, it should always lesser. For series combination and for parallel combination, whatever the answer you are getting, it should always greater than the individual terms. 0.9988. So Pedro, Anu, Murli, only three are responding. Very good, you all are just giving the correct answer. Now for the D problem, For the D problem, that is parallel series configuration, here we have the components having reliability given as 0.90, and then this is 0.98, 0.98, and here we are having two components, that is reliability is given same as 0.90 and 0.98. Now first we will find out the for single term. Suppose we are finding out this left hand side R equivalent, so take it as R equivalent to 1. So how you can write 1 minus 0.90, 1 minus 0.98, 1 minus 0.1 into 0.002. So 1 minus 0.002, 0.998. So final R equivalent will be series of each terms. So we can say it as 0.998 ka whole square of 0.998. So this will comes out as 0.996. So that's all for this series parallel combination problem. No, one question is left. So let us solve the last problem of today's session. And this question also belongs to series parallel combination of these reliability problems. So in this problem, you have to calculate the equivalent reliability of the system shown in figure. Just start individually, like here, divide it for this term, for this parallel configuration. Let's take it as R equivalent 1. So R equivalent 1, how you can find? It is in parallel combination. So R1 minus 1 minus 0.9 whole square. So it will give you 0.99. Now let us take this as R equivalent second. So for this R equivalent second, you can get as 1 minus 0.98 cube. So for this value, you will get answer as 0.9992. Finally, R equivalent will be R equivalent first will is 0.99. So I just want to make one step also. So for series combination, the whole system will looks like that. There are 4 series components, and each reliability having as 0.99. This is 0.99, and this is 0.50, and this is 0.9992. So equivalent reliability of system in 0.9 multiplication of each reliability terms 0.99 into 0.50 into 0.9992. So this will comes out as 0.49. So how many of you are able to get this answer? Yes, 0.49. Anu and Murli both are correct. I hope you all are able to get this. This one is very simple trick. You have to just keep in mind that for series combination you have to multiply the whole each individual terms, and for parallel terms you have to subtract it from a 1 and then multiply like this one 0.98 you have to subtract from minus 1 minus 0.98, and how many parallel terms are there you have to just multiply that. I think you all are able to get it. So this is the last problem for today's session, so I just close today's session. If you have any doubt you can ask me, and if you want any clarification, anything, any doubt, any type of doubt. If there is no doubt, then we can close our session today. Now we are, I think we are in middle of this course, this NPTEL course. Okay, thank you all for joining this session, and we will meet on the next Saturday at the same time.
Thank you, sir.
Uh, okay, thanks.
Thank you, sir.